On March 14, 2013, the LHC delivers.
It was an electric atmosphere. I mean, the 20-year-old physicists had camped out overnight in the hallways to get good seats in the lecture hall. And the 80-year-old physicists who had invented the idea back in the 60s, they were flown in from all over the world. And, you know, secrecy was important. So it was like, this is the one seminar you're not going to want to miss in your lifetime.
I think we have it.
The discovery of the Higgs boson is one of the final keys to our understanding of the Big Bang.
It was a very emotional moment. I mean, people got choked up.
Thanks to Peter Higgs and the efforts of scientists around the world, we understand a key moment of the first second. We now have all the building blocks to make a universe.
1,000 years from now, when they're writing the textbooks, they will remember the moment when we found the Higgs boson. All the matter around us, all the human beings and all the people, all the stars and the planets in the sky, and the Higgs boson was the missing piece. It's what really makes it get up and go.
Without this Higgs mechanism, the Higgs field, that formation of mass, you'd have no atoms. Without atoms, there's no structure. We're not here. That's where this other name for this particle came from, as a God particle, in a sense. We would not exist without it.
Stars, planets, and people would be impossible without the Higgs field and the Higgs boson. But these new discoveries may be responsible for much more than keeping our feet on the ground. When the Higgs field pops into existence during the first second of the universe, some scientists believe it may have triggered the splitting of the superforce.
Without the Higgs boson, we can't exist. And we think that a series of Higgs bosons were responsible for breaking the symmetries of the superforce so that the four forces could emerge. That's why when we found the Higgs boson, champagne bottles were being opened up in all the physics laboratories, and we were all having a grand party.
Next, two final forces split off.
Without the weak nuclear force, the stars would not shine.
The electromagnetic force is the force that governs almost everything that we do, even the chemistry of our own bodies.
The weak nuclear force and the electromagnetic force now stand alongside the strong nuclear force and gravity to shape the universe we live in. With these four forces, we have a universe that can create our home.
The laws of physics which govern our universe are at heart these fundamental forces. These forces drive the evolution of the universe.
The picture won't be complete until we find a way to join the four forces. And the LHC isn't the only experiment offering clues to how it might be done. The BICEP 2 telescope at the South Pole found temperatures 10 million billion times higher than those at the LHC, perhaps hot enough to unify everything.
The BICEP experiment has given us a measurement of the energy scale of inflation, and that energy scale is really high. It's so high that it's very tempting to associate inflation with the unification of all the forces of nature. It's at the energy scale at which we think the basic forces of physics, gravity, the strong force, the weak force, all come together into one grand force.
Today is a new golden age for physics. The discovery of the Higgs at the LHC and gravitational waves at BICEP 2 might help scientists unify the fundamental forces and grasp the true holy grail of cosmology, a theory of everything.
Seeing the detection of these gravity waves, seeing inflationary theory work so well, gives me hope that the program of finding a fundamental theory that unifies all the forces of nature, explains what can happen in the first moments of the Big Bang, might be realized, and maybe even in our lifetime.
We're nearing the end of the universe's first second. The cosmos, now an inferno of radiation and matter, has given birth to the four fundamental forces of nature. But a mysterious form of matter threatens to destroy it all before the first star has a chance to shine. The first second, the most important second in the history of the universe, is nearly over. The universe is now 20 light years across, a fireball of light and matter. But an almighty battle begins to rock the cosmos. Fundamental particles, the building blocks of atoms, fill the early universe. But they must survive a war whose outcome will determine our future. Because matter has an evil twin, antimatter, and the two are mortal enemies.
In many ways, they're opposites of each other. And what that means is, if you take a lump of matter and a similar lump of antimatter and slam them together, they will be totally converted into energy. And according to Einstein's E equals mc squared, it's a lot of energy.
Matter and antimatter simply can't coexist. They annihilate each other on contact. This cosmic carnage rages as billions of times more matter than we see today simply disappears as matter and antimatter collide. The fate of the universe hangs in the balance.
You have to understand, the universe shouldn't be here. It should have been half antimatter and half matter, and we should have all annihilated. We do not understand why we even exist.
At the end of this epic war, matter wins out by the slimmest of margins. But why?
The question is, why in the universe as we see it, there are so many more particles than antiparticles? The galaxies and the stars that we see in the sky, these are all made of matter. They are not made of antimatter.
Somehow, the balance between matter and antimatter was slightly skewed from the beginning.
For every billion particles of matter and antimatter that were being created by energy, one extra particle of matter, and that very small asymmetry of 1 part in a billion is enough to account for all the galaxies and stars we see in the universe today.
Could this have turned out differently? What if antimatter had won the war?
If antimatter had won instead of matter, the universe would probably look the same today. In fact, you know what? We'd be made of antimatter, and we'd call it matter. Anti-lovers could sit in cars, anti-cars, looking at anti-moons, making anti-love, and it would all seem exactly the same.
So why was there more matter than antimatter? Why was the universe built out of balance? Professor Tara Shears at the Large Hadron Collider wants to find out.
What we're really interested in is how different the amounts of matter and antimatter are, and whether they match up to our understanding of how different matter and antimatter should be, because that's what we don't understand.
The LHC results show that the difference between antimatter and matter is smaller than expected. To explain why, scientists need to know what's tipping the scales in matter's favor.
I really hope that we're going to make a measurement here sometime in the future which is going to just show us the light, show us what else there is out there in the universe that's going to make it all make sense.
We still don't completely understand the first second of the cosmos, but the fact that we know so much already speaks volumes about the determination and ingenuity of our scientists.
As a civilization, we are extending our understanding of where we are in the universe. And that's extremely important. This is why we really love doing what we do.
The first second is over. the universe already contains the building blocks of everything we see today.
What we understand from the first second tells us a lot about what's going to happen for a long time after that.
The first second of the universe is amazing in its potential. Here we had a universe with just these fundamental forces and these very elementary constituents of matter. And what would they yield? They would yield an entire universe. They would yield the works of Shakespeare and the music of 50 Cent.
We have gone so much further than anyone believed we could have. And I don't see why the origin of the universe will be any different. It might take 5 years, it might take 500 years, but I really believe that one day we will understand mathematically how our universe began.
In the next few minutes, the universe cools enough for protons and neutrons to form the first atomic nuclei. Another 380,000 years must pass before the first atom appears. In hundreds of millions of years, those atoms clump to form the first stars and galaxies like the Milky Way. More than 9 billion years after the Big Bang, our sun and our planet, Earth, is born. Their fate sealed in the first second of the Big Bang.